Hi everyone, hope you all enjoy your coffee break. I'm Jo from the University of Melbourne, and today I'm giving talk about towards a verified cost model for code by push value, supervised by Christine from the University of Melbourne and Johannes from the University of New South Wales. So, first of all, I'm going to tell you why I'm looking at cost models specifically, why is it important, and then I'm going to talk about how I'm going to come up with this cost model, which is why I need to verify the cost model, and also why code by push value specifically. Okay, so now let's look at why cost model. Oh, sorry, and at the end, I will talk about my project, about what my plan is, and what I have done so far, and what future work could be done. Okay, so as we know, there are different programming languages. Some are imperative, such as Python, Java, C++, and some other ones are declarative, actually, and some of them are functional. So it includes Haskell and standard ML. And what we're interested in today is the functional programming languages. So functional programming languages, they have the advantage of they don't need to specify the low-level details of how programs should run on a computer. And in fact, it provides a very convenient way to us to describe what programs should compute to in a concise mathematical manner. And thus, it's really nice abstract representation for us to reason about things such as the proving the program's correctness against its specification. So, given all these advantages of functional programming, there are two important things to notice. One is that they must be correct, like it should give us the right output. And then we also know how long and how much space it will take for it to give us the correct output. So, which is the computational complexity in this case. And I will refer to them as cost in this plot. So, in order to get cost of functional programs, we need to have some sort of algorithm. And such an algorithm will be called cost models. And how are we going to get cost models for functional programming languages? So, as I talked before in my elevator pitch, so if we need to write cost model for each different programming languages from scratch, it will be kind of annoying because you will have some repetitive work. But due to their different nature, since different functional programming languages have different evaluation strategies, we do have to have very different cost models, in fact. And so that's when we need to look at Lambda-calculus. So Lambda-calculus is the foundation of functional programming languages, and which means if we can get a cost model for Lambda-calculus, we can then extend that for those languages, and that will make our work a lot easier. Okay, so that's why we're interested in cost model for Lambda-calculus. And next is why verify those cost models. So traditionally, all the proofs have been done on pen and paper, but in the recent decades, we have more tools to help us to do proofs. One of such is interactive theorem prover, such as Ho4, Koch, and Isabel Hall. So those interactive theorem provers, they have the advantage of it helps us to do our proofs, as in it can double check if our proofs we've entered so far are correct or not, because we know we're human, we make mistakes, and that actually happens a lot. And those theorem provers are really helpful in that sense. And also it allows us to reuse others' proofs a lot easier. We can just import the proofs other people have done in library, and we will use them again, and we know they must be correct since it's being checked. It's being machine checked. Okay, so that's why verify the cost model. And in the end, why code by push value specifically? What even is code by push value? So going back to Lambda-calculus, I mentioned earlier, there are different evaluation strategies for the functional programming languages, and that is there are different evaluation strategies for Lambda-calculus. So there are weak and strong Lambda-calculus, where the weak ones, the reduction doesn't go under the abstraction. And we also have things like code by value, where the arguments are always evaluated first before a functional call happens, or code by name, we substitute first, which is we do the function call first before we evaluate the argument. And call by need, which is lazy and doesn't evaluate things until it's absolutely needed. So, as you can see, all these three different evaluation strategies will, for the same piece of program, it will produce a very different way to evaluate down the same given program, which means the cost in terms of time and space will be very different given different evaluation strategies. And that means we will need different cost models for different strategies. And is there a way to do them once and for all instead of coming up with different cost models for different strategies every time? And the answer is yes. There is another thing, another strategy called call by push value. So it's proposed by Paul Levi, and so call by push value uses something, uses the pair thunk and force to let the user freely decide when they want to evaluate the arguments. So instead of always evaluating it first or always substitute first, they can thunk the evaluation temporarily and force it when they want to evaluate later. This means using call by push value, we can actually simulate call by value and call by name and call by needs and things like that. So which means if we can have a cost model for call by push value, we can extend it to cost models for call by value and call by name. So coming to my project, I'm interested in cost models for Lambda-calculus and in fact call by push value Lambda-calculus. But how am I getting there? How am I going to get to my cost model, and how do I know if my cost model is correct? So that's why we need to bring in Turing machines. So as we all know, hopefully we all know, Turing machines is another model of computation which is equivalent to Lambda-calculus. And so how it's going to work is there's a notion called reasonable. So we say a machine is reasonable if it can simulate and being simulated by a Turing machine in with a polynomial time overhead and constant space overhead. And this is what I use to show my cost model for Lambda-calculus is correct. So that's reasonable. And I will do that for call by push value. So how am I going to do it? How am I going to achieve it? How am I going to show that my cost model will be a reasonable one? So there's work being done by Forster, Kuze, and Roth in 2020. So they showed that with call by value Lambda-calculus, it in fact has a reasonable cost model for both time and space. And how they did it was really interesting. So instead of going from Turing machine to Lambda-calculus straight away, which is quite a big gap because we all know Turing machines are like states and case, and well, Lambda-calculus, Lambda x and y, which is kind of different. So in this way, they come up with some intermediate machines called abstract machines. In their method, they use a machine called substitution machine and another one called heap machine. So by going through these machines, they made an easier transition than just jumping from Turing machine to Lambda-calculus straight away. So what I want to do is similar, but instead of with call by value, I want to make it true for call by push value. And so to summarize, I want to show that my cost model for call by push value on the calculus is reasonable by going through some intermediate machines, which is the blue box here. And what I have done so far, one part is porting. So as I mentioned earlier, there's been work being done for with call by value. And so I ported that work and also their earlier work into whole 4, from COP into whole 4. And in fact, you can find my whole call by value reasonable one on my GitHub profile, and you can also find that in the whole 4 library. It's being merged into the whole 4 library as a pull request. And I'm doing this because one thing, COP and whole 4 actually has different logical foundation. So it would be really nice to cross-check if the thing works in COP still works in whole 4. And also, I have 4 years of experience in whole 4. I've been doing lots of whole 4 verification since I was in undergraduate. And lastly, it will benefit the whole 4 community, allowing people to reuse that in the whole 4 library as well. Okay, and the other thing I've done is the time cost model for call-by-push value. So first of all, I formalized the call-by-push value lambda calculus in whole form, and in fact the untyped one. And then I also defined and formalized the substitution machine for call-by-push value, and also defined a compile function that can compile call-by-push value lambda terms into substitution machine terms, which I will refer to as programs here, programs for the machines. And I also showed the that substitution machine can simulate call-by-push value lambda calculus with a reasonable time. And here, just like a small show up of my code. Understand right now, like, give me 1 second. Okay, jokes aside, I just wanted to show you quickly the definition of my substitution machine. And as you can see, since it's called a substitution machine, so it just does substitutions right away. So for instance, my application, the rule for my application here, so when my stepping rule sees the application, it just does a substitution. That's essentially what I wanted to show in this phone talk, because I don't want to bore you with too much technical details. If you're interested, everything should, wait, is everything, maybe they're not on my GitHub, they're not public yet, but you can find my proposal, you can find my paper and have a look. Okay, so also just to quickly show how it worked for my proof of time. So it's essentially, if I have a lambda term called s in call-by-push value, and it can step into the term t under the stepping rules for call-by-push value in I steps, then inside the substitution machine, once I compile s into a program in the machine, it should also be able to step into another program that represents t using the stepping rules for the substitution machine under pi, which is a polynomial of I. And so this is what I showed. And so yeah, in conclusion, my contribution would be, once I've finished everything, I will have a cost model for call-by-push value lambda calculus, which is reasonable. And I will also have it verified in whole form, so that we can extend my cost model into the ones for call-by-name, call-by-value, etc. And also, so we can extend them for different programming languages based on like call-by-name or call-by-value. And then we can have cost models for them instead. And another interesting future work would be verifying efficient compilers using things like HickML, but that will be a long story after. So yeah, and these are my references. Yeah, so thank you so much, and I think I might have finished a bit early.
That's right. Thank you.
So, any questions? Yeah?
So,
do you mind or?
Oh, do you need to mic me up?
I can repeat the question, I guess.
Yep. Okay, cool. All right. So I'm not really a Lambda-calculus guy, but it looks like the call-by-push value Lambda-calculus is like the assembly language of like Lambda-calculi, right? And so like you're building like a cost model that would help you reason about that. And then, given the other, what I think of as higher level Lambda-calculi with the different evaluation strategies, right? Then presumably you would have a way of relating those, like some sort of simulation theorem or something like that between those and their encoding and call-by-push value. Does the reasonableness of your cost model then allow you to kind of have to sort of more easily show that that simulation would preserve the cost model, or would you need a separate proof? Like if you had like suppose I've got my program in, I don't know, call by need or whatever, right? And I want to use your cost model to reason about its, complexity or whatever, right? Does the reasonableness of your cost model help me, or would I still need some sort of, to show that my simulation is sort of cost model preserving or something? I don't know if I'm making any sense.
Right, so you're asking if I have this cost model for code by push value, and when you are wanting the cost model for code by need, can you use it straight away? Or
Yeah. What would I need to do, basically? Like, yeah, and does reasonableness help me at all, or like yeah, I don't know.
Right, that's a good question. So for the purpose of my project is that if I finish this cost model for code by push value, then you should be able to once you can show that we can use code by push value to simulate the code by need strategy, then you should be able to extend my cost model to use for your code by need cost model. And if we need to verify it again, I guess, so the reasonable is a definition for whether my cost model will be able to simulate Turing machine. And so what we want for code by need will also be, we want to show that the cost model for code by need is also reasonable, to show that we can actually use it. We want to show that it's reasonable, like we can simulate simulate Turing machine with a polynomial overhead in time and constant overhead in space. So in that sense, what do you think? Can we use it straight away? I think we do need to extend it and maybe have some small proofs about. Yeah, I think we do need some sort of proofs to show that between our cost model and code by need cost model, it will preserve the complexity. But that will be a lot easier than proving from Turing machine to code by need again and again. Yeah.
Gotcha.
Yep.
Really random question. How does your system handle recursion?
How does my system handle recursion? That's a good question because right now it doesn't handle yet.
Yeah. Any ideas?
I think I need to maybe think about any typed code by push value first before I think about recursion.
Is that like simply typed Lambda-calculus?
So right now I'm working on typed code by push value. So another thing for code by push value is so the typed code by push value it actually separates separates the force and thumb things into different things. It has two types, one are like values and one are computations. And the values are not the traditional values like variables, but it also includes lambda abstraction, and thumb will be a value. Actually lambda may not be, but thumb is a value. And
Lambdas aren't values?
Yeah, which is weird. So so that is how the typed code by push value is. So it's a bit different to what you might think in terms of typed Lambda-calculus. But yeah.
That makes sense.
Yeah.
Okay, I have a question. Is the definition of reasonable transitive? So I mean, so for example,
transitive.
Yeah. So for example, if you say that your cost model can simulate a Turing machine, and there's another model, for example, code by need can transition your model. Does that just implies that the code by need model can simulate the Turing machine?
Right. So you're asking if my model is reasonable against Turing machine.
Yeah.
And code by need is reasonable against my model. Like, can I say code by need model is reasonable against Turing machine as well? That's a very good question too. So actually, I'll go back to the definition of reasonable. So reasonable is basically two reasonable machines should be able to simulate each other within a polynomial overhead in time and a constant overhead in space. So, and Turing machine has shown to be a reasonable cost model. So, which means by using this, definition of reasonable, we can see that if we can show my model is reasonable, then it is a reasonable model, and then we can also, if we have code by need reasonable against my model, then it is also reasonable. So yeah, it is.
Okay.
Oh, yeah.
Sorry. So assuming that a Turing machine kind of approximates what like a real computer does, right? If the cost model is polynomial in time.
If the cost model is polynomial.
If your cost model is if translation is reasonable.
Yeah.
And you have a cost model on the other side.
cost model for callback push value.
For callback push value, yes. Then shouldn't I be worried that a polynomial translation to a Turing machine will kind of give me a wrong idea of how costly my program is, because some things might suddenly become polynomial when they are executed on a real computer, and others might stay the same.
I think it goes back to the definition of reasonable as well. Since we know it always has to be a polynomial overhead, then it wouldn't surprise us if we set that to be part of the definition.
Oh yeah,
I don't know if
sure.
that
But,
answers your- I don't know.
right. I guess. I mean, maybe this is the best we can do, right?
Yeah.
But like, could there be a better way to like really say, okay, this is exactly how much it will cost to run on a Turing machine, rather than within some polynomial of it.
All right, that would be hard, I think. So what I'm doing so far is all between the abstract machines to come back push value yet. So I'm not sure how accurate it will be going down all the way to Turing machine. But actually, the paper I referenced before, the same authors, they actually have another paper where they actually verified everything from Turing machine up to weak callback value Lambda-calculus. Where was it? Right, so yeah, here. So what I mentioned, the paper I mentioned for them was the one where they showed that the simulation between abstract machines and Lambda-calculus improve in the solver, and then the rest on kind of paper. But later they actually had another paper, which they verified everything from Turing machine all the way up to weak callback value Lambda-calculus in terms of time. So that might be something you would be interested in for your question. Yeah. Thank you. Yeah.
So when you're done with the, you talked a lot about proving theorems, and I understand that's kind of the main body of your thesis work. But when you're done, you'll have a way of, modeling the cost of programs. The practical value of that is that people can use it to verify programs. So have you thought about evaluating how you will evaluate that?
How I will evaluate?
Are you going to, in your proposal you said you would do some work applying your cost model to actual programs.
Yeah.
Right? Have you thought about like the selection of those programs, how that would demonstrate, that your cost models are useful and practical and
What was the last part? Switch to different.
have you thought about which programs you will apply your cost model to?
Oh, so have I thought of what examples I'm actually going to apply my cost model to?
Yeah.
Right. Also, first of all, I need to decide which language I'm going to extend my cost model to. So I need to have a cost model for that language first. Then I use that for the program in that language. I haven't thought about it, but since my favorite language is Haskell, so I think I might try with Haskell first. But maybe a simpler one.
Yeah.
Do you have any recommendations since you asked the question?
Okay. I don't have concrete recommendations. I just encourage you to, I'd encourage you to think about that early.
Yeah.
Think about, what language you might want to do it in. I mean, Haskell would be fine. It could also just be, call it push value. But think about, I think maybe more think about the language, the programs you want to verify, right? What kind of diversity of programs would be kind of sufficient to show the value of your approach?
Yeah.
And I think part of the point is if you do that early, you can kind of look at those programs as you're developing your system and kind of use them as motivation and make sure that the system you prove correct is also going to be useful when you go to evaluate it at the end.
Yeah, that's true. I probably should come up with programs I want to check against once I finish my skeleton for cost model. Yeah. Thank you so much for this advice. Yeah.
So maybe this is a comment rather than a question. I think as far as I understand, the original call by push value calculus models can model call by value and call by name, but not call by need. there is I saw a paper
Mm.
about an extension of the call by push value to call by need, to model call by need.
Right.
Which one are you working on?
Oh, so you can definitely simulate call by name and call by value since it's already established in the book
Yeah,
for call by push
that's right.
value.
Yeah.
Call by need is lazy. You should be able to maybe with possible extension as you said in that paper. But since so far I'm only looking at call by name and call by value. But I think call by need should also be able to simulate as well though. Since we can delay our evaluation until we need it. So it's similar to we've done for call by
I
need.
just saw one paper about an
Okay.
extension of
Okay.
the original calculus
Uh-huh.
to deal with
Uh-huh.
call by need.
Right.
I don't know whether you definitely need such an extension or you can encode in some way
Right.
call by need by the original calculus. I don't know, but it seems that you need some another technical device
Mm-hmm.
to model call
Are
by
you
need.
recommending the paper after?
Sure, sure.
Yeah, thank you so
Sure.
much.
So if your favorite language is Haskell, you,
Yeah.
you may need.
Call by need, yeah. Yeah,
Right.
thank you.
Okay. Do you have any other questions, comments? No. Nick? Oh.
Okay.
Can you say a little bit more about, so one thing I think would be helpful for me to understand is why you need both a verified cost model for call by push value and a connection to Turing machines. Because it seems like if I have a cost model for Turing machines and I have a cost model for call by push value, don't I automatically make a connection between those?
Oh, so because reasonable is defined by showing that it can simulate Turing machine. So it's not a standalone definition. It's like a comparison definition by comparing that in.
So is the issue that the primitives and the cost models are different?
So it's, sorry, I'm not sure.
My understanding was that you need to show that it respects the Turing machine.
Yeah, to show that.
In order
it's
to
reasonable.
show that what you've done is actually correct.
Yeah, so I need to show the polynomial overhead and constant space overhead between Turing machine Lambda-calculus cost model to show that my one is reasonable as well. So we know Turing machine is reasonable, and in order to show my one is reasonable, I need to show it against the Turing machine. That's why we need two things. Yeah.
Okay. How is the Turing machine proven reasonable? Is that with respect to something else?
I think just one of the fundamental things that is established. Actually, there's
Or is that
about
like the
Turing
base
machines
assumption?
and RAM machine. They are reasonable machines. They can simulate each other.
Okay,
And
so it's like RAM machine versus Turing machine. Did you think about targeting the RAM machine instead of the Turing machine?
actually, I thought of that too. But so far, I'm just working on the abstract machines, and in the future, maybe RAM machine could be another potential layer between Turing machines and my abstract machines. But yeah.
Just a further question, are there other Lambda calculuses that have cost models that are reasonable?
Out there?
Yeah.
I mean, yeah, we call by value Lambda.
Yeah, so why don't you simulate it in call by value? Because that would sound easier because they're closer together.
Because it's call by value, it's like we are able to construct call by value using call by push value.
But you can't simulate call by, you should be able to simulate this because everything's equivalent computationally with power, you know? I'm just curious if that would be harder to simulate.
But then everything call by value was still based on call by value, which is not what we really want to. Because call by value and call by name wouldn't be able to simulate each other. I mean, it'd be
like they can, you
constructing
can just
them.
write you can write a Turing machine in call by name and then convert yours to a Turing machine and then you've got everything in call by name. Like,
it may not be a reasonable.
yes, of course. But then the question was if it would be difficult to get reasonableness
From
call by name.
call by name.
Like an implementation of call by push value in call by name would that be hard to be reasonable?
I feel like because my purpose using code by push values, so you can simulate code by name and code by value.
Yeah, you don't
But
want
when
to
you
end
code by
up
name,
building it on
simulate
top of each other.
code
Yeah,
by
that
push
makes
value.
sense.
Yeah.
Okay.
Okay.
Thank you,
Yeah,
Sarah.
thank you so much.